All right, research methodologies, folks. This is our video on shape, center, spread, and outliers. And so what we're going to be doing is we're going to be talking about distributions. So let me actually begin. Let's talk about what a distribution is. So the distribution of a random variable is the manner in which a set of quantitative data is spread out through its range of values. So we're going to characterize a distribution of a quantitative variable using four common characteristics. And they're going to be your spread, your shape, your center, your spread, and your outliers. Okay, and they all kind of work together in order for us to kind of characterize a distribution. So the first thing we want to do is we want to think about how is it that we create or construct a distribution, because that helps us to understand what a distribution actually is. Sometimes it's kind of hard to imagine what a distribution is if you haven't gone through and constructed one. So let's take a look at that. So let's suppose we have this question where we want to determine if including bed rails at a skilled nursing facility would decrease the number of falls that patients will experience in a year's time. So what we get is we get over here, we're going to get a set of variables. Okay, those are our number of falls, and we collect data, and so each one of these data elements is from an individual. So we've got patient number 1 had 0 falls within its 6-month time. 1 fall for patient number 2. Patient number 3 had 3 falls, and so on and so on and so forth, and we go out and we collect data. Now this thing right here is called a dot plot. And so what a dot plot does is it's going to put a dot inside of each value for the number of falls. And what we'll do is we'll see, right, basically how our data is distributed, all right? And I don't know, maybe it's not an air quotes thing. It's distributed, right? How is it put on those values for number of falls? So what we see here is we've got 0. 0 has two patients that had 0 falls. We have, in this case, 5 patients that had 1 fall. We had 4 patients that had 2 falls, 2 patients with 3 falls, 1 patient with 4 falls, and 1 patient with 5 falls. Okay, so what we see is we see that we can put our data, right, inside of some kind of order. Okay, so like I get the 0 and it goes pop right onto that one, onto the zero placement. So the dot plot is a very simple way of showing what the distribution looks like. Okay, and that distribution again is just a way of placing our data to kind of help us make sense of it. Now, let's suppose that instead of like a very small data set, 15 data points, we get larger data sets. So in this case, we'll utilize something like a histogram. And so as we increase the number of data points, right, what we have to start thinking about is we have to start thinking about in what ways do we group our data, in what ways do we like kind of place our data onto a data set, right? And so we're looking at, in this case, we've got our no bed rails example, and that is individuals who did not have bed rails and how many falls they had versus the group that had bed rails, okay? And what you can see here is that in the group with no bed rails, right, we still have quite a few that had 0 falls, okay, and a good group with 1 fall, and a big group with 2 falls, but we also had one person over here with 8 falls, right? Which probably at some point in time you'd say, look, we can't have that individual. They'll end up getting hurt, and we can't have them there. You can't really see this because it's got my picture on it, but what you'll notice over here on this one with the bed rails example is you'll notice that we have 1 fall, right, or 0 falls, then 1 fall, and so the majority are in the 0, 1, then the 2, and then finally the 3, and we don't have any person who has more than 4 falls, or 4 or more falls. Okay, so the majority of the ones with the bed rails group, right, have either 0 or 1 fall, right? And so those are like numbers of patients, and that kind of tells us something about the distribution of falls amongst the individuals who have bed rails. So what this does is it says something about, to what extent are the bed rails effective, right? I look at the bed rails example, and what it has is most of the values are in the 0 and 1. Okay, we have very few large numbers of falls. Whereas in the no bed rails, we're going to notice some things like about it being more spread out and the like. Okay, and that's just, kind of like, oh, that what we're doing here is we're just placing our data onto a graph of some sort to help us see which values have higher frequencies. Okay, So let's talk about how we construct a distribution, because that should also help us think through how distributions work. So each quantitative distribution has its smallest values on the left and its largest values on the right. So it kind of works in terms of like the number line. So the number line goes from smallest to largest. Okay, and so actually I should say smallest to largest because I mirrored. Those range of values of the variable will be the two ends of the distribution. So the value that is average of the largest and smallest values is called the mid-range. So you imagine you've got the smallest value and you've got the largest value, and those get placed on the distribution. And if we average the two of them, right, add the two together and divide by 2, right, the very middle of it, that's what's called the mid-range. That's the center of the graph. That is not actually going to end up being what we call the center, right? But it will be a way of thinking about the picture representation. So if we had 0 as our smallest value and 100 as the largest value, the mid-range is going to be 50, okay? And that just helps us think about how the distribution is set up. The mean, the median, and the mode of the distribution do not necessarily need to be in the middle of the graph, and that's why we want to distinguish about what the center is, because that mean, the median, and the mode, they could be anywhere on that graph. They could be in any location depending upon external factors. And so consequently, we don't want to think about them as the middle. We want to think about that mid-range as the middle, and these values, the mean, the median, and the mode, as the center. So we go in, we look at, here's the construction of our distribution. On one end, you can see that we've got about 125 as the lowest value, and the top end value is 350, okay? And so right smack dab in the middle is around 250, or actually it should probably be about 225 or 235, and that would be right smack dab in the middle, and that's our mid-range. Notice most of the values are not in the middle of the distribution. Instead, they're over here at 150 and 175 and 200 and those areas in there, in between 150 and 200. Okay, so clearly, right, when we talk about the middle of a graph, that middle of the graph, it really doesn't have a ton of meaning other than the picture has a middle. It's right there in the middle of the graph. Now, let's talk about measures of center. Because we talked about the middle of the graph, now we want to talk about measures of center. So we'll have 3 different versions of the center of a quantitative data set. The first one is the mode, and it's really only meaningful for ordinal data. So we're not going to really talk much about the mode today. Okay. The second one is the mean, and that's the average of all of the elements in the data set. It's the average, right? We talk about the mean, the average. They're basically the same thing. And then we have the median, and that's the dividing line between the smallest 50% of the data and the largest 50% of the data. Okay? And so when we talk about 50% of the data, if you've got 200 elements in your data set, right, or 200 members of your sample, the bottom 50 values that you get, okay, are going to be your bottom 50%, and that median is going to cut right there at that bottom 50%, and then the top 50, right, are going to be your top 50%. Or, just so that we don't think 50-50, let's imagine that instead we have 180, okay, 180 data elements. So our 50th percentile, that we call it the median, is going to separate the bottom 90 values from the top 90 values for the value of what we call the variable, okay? And so that's going to be like kind of how we think about a median. Now, when we look at a distribution, the mean, which is going to be in my green, okay, and the median do not need to be in the same place. So in this case, you can see that the mean is around 200, and the median is like slightly less than it. It's going to be about 190. So that means that the bottom 50% of the data, right, is cut off at 190, and the top 50% of the data goes from 190 all the way up to 350, okay? So what we see there is that that top 50 is more what we call spread out, right? It's going down from 190 to 350, whereas the top half really is about from 130 to 190, okay? And it's more scrunched up. And that's because we have these 2 really big bars and a third bar that's, you know, kind of mid-sized, right? Whereas in the bottom half, we just have 1 big bar, then we have 2 smaller bars, and then we kind of just taper off towards the end, right? So there's our median. And our mean, right, is what we're going to see is it's pulled, right? It's going to end up being pulled, and it's pulled towards what we call the tails, and we'll talk about the tails in a little bit, so that mean ends up being larger than our median. So that actually leads us to this idea of a skewed distribution. So we've got this difference, okay, this difference between the mean and the median, all right? And so we're going to imagine that the median is kind of like our dividing line. It's 50-50 in terms of percentile, and it's a special kind of value because it really doesn't get affected as much by, say, for example, the spread of the distribution or other things like that. It kind of is pretty steady, okay? But our mean can actually be pulled in one direction or another. And that's how we end up getting skewness. When we talk about skewed, something being skewed, we're talking about in which direction is the mean pulled, okay? So if I look here and I see that this is skewed left, you can see that the mean, the green line here, is actually going to end up being less than the red line, right? It's being pulled, and we say it's pulled towards the tail. That tail piece is this piece right here where we have, it basically looks like a tail, okay? And what that is it's essentially saying that these smaller values have a big influence on the value of the mean, and so that mean, which is the sum of all of our values, gets pulled in that direction. And so hence that gives us skewed left, right? Skewed left, we're going to be pulled in the leftward direction. On the other hand, when it comes to skewed right, okay, skewed right, what we have is we have a tail on the right-hand side. So we have a tail on the right-hand side, and what that means for us is that means actually that we are going to end up having our values, okay, our values are going to be pulled in that right-hand direction because those big values, like in this case, 10, 11, 12, 13, right, are going to pull and they're going to add a lot to the sum, and that actually ends up pulling our average. So our average goes to the right, and that's what it means to be skewed right, okay? Now, so we've got, on the one hand, if we have lots of our data up here at the big values, okay, then the smaller values are going to skew the data left. So lots of values on the right, the mean goes to the left, we have skewed left. On the other hand, if we have lots of data on the right, okay, and we have big values on, lots of values on the left and big values on the right, then what we get is we get that skewing right? We get the pulling right from those large values, and we end up calling it skewed right. And these are our first introductions to the shape of these distributions. So on the one hand, you have the skewed left, right, which has a tail on the left and lots of values for the distribution on the right. And then you have the skewed right, where we have lots of values on the left and our tail on the right. So one way to easily remember this is wherever your tail is, okay, that's the direction of your skewness, if in fact it is in fact skewed. So let's talk about this and kind of review that shape and center. In a skewed left distribution, the mean is smaller than the median. So there are a few small values in the distribution that will decrease the size of the mean relative to the rest of the distribution. And what we say is that these values skew or pull the mean left. On the other hand, if we say something is skewed right, we mean that the mean is larger than the median. There are a few large values in the distribution that will increase the size of the mean. So basically we're moving towards that right-hand side, okay? And so we say that these values skew or pull the mean right, okay? One way to think about this is, say for example, if you're looking at income, and so, most people are kind of in the, I don't know, $20,000 to $120,000 range in terms of income, for the most part throughout the United States. Let's say you bring in somebody who has an incredible amount of money, they're a billionaire of some sort, and you put them into the set, right? Okay. Now the average for that set has become very large, okay? Very, very large, in fact, right? Because now you've taken everybody who's kind of bunched up around $20,000 to $120,000, and you've added billions, okay? And then you're going to divide through by the additional member, but that's going to make almost no difference. What's going to happen is that your average is just going to go way out. It's going to skyrocket. It's going to get really, 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 really large. Really large, okay? And so consequently, that outlier, what we'll call an outlier in a little bit, or that really large value for income is skewing your data right? It's skewing your mean right. Now, Our ideal look, actually, and the one that we have the most math for, is what's called a bell-shaped or a normal distribution. And when we talk about something being bell-shaped or normal, what we're talking about is that it essentially has most of its values around the mean or the median. The mean and the median are essentially in the same place. There might be a little bit of skew one way or another, like in this case. But if you look at the distribution, what you'll see is that we've got most of it around the middle, and then as we go towards the small values and the large values, they decrease. And what we get is we get something that looks like a bell. We get a bell-shaped curve, okay? Does it have to be a perfect bell? No. This one's not a perfect bell, but for the most part, it's got most of its values around the middle, and then it tapers off as we hit the sides, okay? Now, because the values for the data are evenly distributed, the mean and the median are in the same place, and that means that there's no skew in the shape either. No skew in the shape, no skew in terms of the mean, right? A little bit, but not much, right? In this case, where we're looking at height, you can see that like the median is 70 and the mean is about 71 or 70.5. It's a relatively small amount in terms of the difference in heights, okay? And in addition to that, these normal or bell-shaped distributions end up being really valuable for us because if we're going to select a member of the population at random, then what we're going to do is we're going to expect that they're about average because most of the data values are around the average. So most of the individuals in our data set, population or sample, are going to end up being somewhere in that middle range. So if we look at, now we're going to talk about spread and shape. And so the spread of the data is how spread out the data actually is. So for example, if I look at something like this, we'll look at this bell-shaped curve, the one on the left-hand side. And on the left-hand side, what you're going to see is you're going to see a data set that's spread out, but not incredibly spread out. Its data values go from 64 to 76. So consequently, it doesn't have like a huge set of values. It's in terms of heights. So that goes from 5 feet 4 inches tall to 6 feet 4 inches tall. All right. Then we'll look at the one on the right, and on the right-hand one, what we're going to see is we're going to see a set of data values that go from essentially like 53, or what is that, 4 foot 5 inches tall, all the way up through like well over 7 feet, right? And so what we're going to say about the one on the left-hand side is it's got a spread of a certain kind, but the one on the right-hand side has a far larger spread. It's got a larger standard deviation. It's got a larger variance. It'll end up having probably a larger interquartile ratio, although hard to say at the moment. And what we know about it, though, is that it's more spread out, right? It's got more small values and has more large values, whereas the one on the left-hand side, okay, is pretty much going to be, you know, contained within a fairly average range of data, all right? Now, when we look at spread and we talk about how valuable spread is in terms of understanding our distribution, basically what we want to do is we want to think about how predictable is it that, how predictable are our data value, or how much prediction can we make in our data set based upon what we know about the data set. So the more spread out the data is, the less prediction that we can make, right? We have more what we call randomness, we have more variance, or what we call variance. And so essentially what that means is that we have less of an ability to predict the data values if we picked one at random. So a way of thinking about this is to think about it from the perspective of, let's say I am going in and I have a data set that has all the same values for the data. 1, 1, 1, 1, 1, 1, 1, like all the same values for the data. Okay, so every value in the data set is 1. In this case, it has a standard deviation of 0, a variance of 0. It has no spread. Okay, and if I were to pick a value at random from that set, what I would get is I would get 1, simply because that's the only value that's in there. So the fact that there's no spread out of the data means that I have perfect predictability. On the other hand, say imagine a more spread out set where we have values that go from 0 to 150, and in our data set we maybe have 150 values, and every single member of the data set has a different value. So it has a value from 0 to 150. In that data set, you can imagine, okay, if I were to pick one at random, how likely is it that I'm going to predict what value I'm going to get? Well, it's a lot less likely, and that's because the data is more what we say spread out. Right? It has a larger standard deviation, it has a larger variance. So let's talk about some principles for spread and shape. So the range, the standard deviation, the variance, and the interquartile ratio are going to be the most commonly used measures of spread. And that spread of distribution tells us how spaced apart the data values are in a sample or a population. Populations and samples that have data with large spread values are unpredictable because they take on a lot of variables over a large area. Hence, when we are running tests or doing anything where probability is a concern, we would prefer samples or populations with smaller spread, and that's variance generally. Now, you don't have really any control over your spread, right? Okay, any more than you have the shape of your data if you're just taking the data or you're looking randomly at a population. But from our perspective, it's better if we have things that have smaller standard deviation or smaller variance, right? And if you're doing any kind of prediction, you really want smaller standard deviation and variance. Now, the last piece of our distribution that we want to look at are outliers. So data sets with outliers have a significant impact on the mean, the variance, and the standard deviation. However, outliers will not have a large effect on the shape, the median, or the IQR of the data set. So the mean will be skewed or pulled in the direction of the outlier, and we're going to take a look at a picture of that in just a moment. And the standard deviation will be increased significantly because the data will now be more spread out. Okay? So because the outlier is only a single or a few elements, the median, which is a percentage of the data, and not dependent on the sum of the data values, is not going to be significantly impacted, and we'll talk about the value of that. So let's take a look at a data set. The data set on the left-hand side has a few values, the pink values, that happen to be outliers. So notice this is height. And so if we think about in terms of inches, height in terms of inches, we have 80 inches, right? And if you think about that, what's 80 inches? 80 inches is 6 feet 8 inches tall, and that's really tall. Okay, we also have another one that's probably around the 82 inches, so that's getting 6'10". Then we have 84, that's 7 feet tall. And then we have a group of individuals up around 88 and 90 inches, and those are very, very tall individuals. Now take a look. We get some change in the shape, but not a huge amount, right? Still, most of our data values are still kind of in the center, around the middle. But if you actually could take a look at our mean's being pulled in the direction of those outliers, right? Those pink values, our outliers, are pulling our mean. If we look over here on the right-hand side distribution, that right-hand side distribution that does not have the outliers, okay, has the mean and the median pretty much in the same location. And we just don't have that same skewness, that pull of the mean. Median pretty much stays in the same place, but the mean now has gone back in towards the median, okay? And if you look here at the left-hand distribution, the one with the pink values, you'll notice how much more spread out it is than the one on the right-hand side, the one without the pink values. So that actually leads us to the idea of robustness, okay? And so robustness basically has to do with the reliability of a particular descriptive statistic. So because the mean and the standard deviation are so affected by outliers and the shape of the distribution, this means that they are unreliable as descriptions for a data set if we have outliers or non-bell-shaped distributions. So anytime you have a skewed distribution, skewed left or skewed right, for whatever reason, the mean and the standard deviation end up becoming problematic. Okay? The median and the IQR are not affected by the shape of the distribution or outliers, so they are more reliable for a variety of different kinds of distributions. Right? So we end up having those be the more reliable ones. So how reliable a statistic is called its robustness. So for this reason, we say that the median and the IQR are robust, and the mean and the standard deviation are not. So if I'm going to select my measures of center and spread, here are two pretty good ways of thinking about this. So the mean, the variance, and the standard deviation are the best measures of center and spread to use for doing inference because they're the most versatile. We have the most math for them, actually. However, their lack of robustness means that we have to modify the data set or make sure that we are working with a bell-shaped distribution that has no outliers. If we have a distribution that is skewed or has significant outliers, we will choose to use the median and the IQ for our data sets. And this is because essentially what we have is we want to use things that are more reliable. We want to be able to actually be able to rely upon our conclusions. And in the case of skewed data sets or data sets that have large outliers that we don't remove, the median and the IQR are actually our best statistics. So this completes our conversation about the shape, center, spread, and outliers and how they all kind of work together. What I want you to do is I want you to kind of think along the lines of, or kind of picture how everything kind of works together to give a description of the data set. For me, that's actually pretty crucially important. All right, this concludes the lecture.